Good afternoon. So starting lecture 48, we shall continue our topic on MOS modeling. Let me have a recapitulation of the lectures in the last two classes. A very quick review. We started our topic on MOSFET modeling, and I said that the MOSFET models were developed in various stages along with the technology, and the level 1 is the simplest, which is based on the assumption that the depletion layer is horizontal, so that there is no drain induced depletion created, which makes things very simple. You remember that these are the expressions for VTH, which was already discussed. The flat band voltage was this, and ultimately we could write the current in level 1 in a very simple form, which was derived earlier. Please remember that here the second suffix indicates source. That means all voltages are measured with respect to the source. VGS means between gate and source. VDS means between drain and source. TA stands for threshold. COX dashed indicates the oxide capacitance or the gate capacitance per unit area, whereas we shall see afterward, if this dashed is removed, it indicates the total oxide capacitance. Okay, total oxide capacitance, input capacitance is COX, whereas COX dashed or prime indicates the capacitance per unit area. So this was a rather simple expression, and we indicated what are the geometrical definitions of L effective. L, I said L is the gate length defined in the mask. L is a gate length defined in the mask. L effective is the effective channel length between the two junction edges, source substrate and substrate drain. And when the MOSFET is in conduction, you remember that a region near the drain is pinched off, and if L dash is the distance of the pinch off point from the source end, then at this point normally we assume that Qi is equal to 0 in the second model. Xj1 is the extent of lateral diffusion, whereas Xj is the vertical diffusion junction depth for the source and drain. Source and drain otherwise are identical. We define in level 1 VDSAT in a very simple way. We said that near the drain end at the point L dashed, that is the point of pinch off, the voltage is VGS minus VTH. That means the voltage at the gate with respect to the point of pinch off is VTH, and that is approximated as VDSAT. That is approximated as the saturation voltage for VD, beyond which the current even becomes saturated, and that is a simple definition of VDSAT in level 1. So substituting the value of VD, which is VGS minus VTH, in the simple model equation, which is valid for the linear region, we get the current in the saturation region, where beta is a parameter defined like this, and in this mu COX dash is usually an important parameter of the spice, and that is normally denoted by Kp. This is called transconductance parameter. Here we saw first model, the level 1 assumes that the current in saturation is related to the square of the difference between the VGS and threshold voltage. Okay, that was rather simple. Then we came to the actually the integration of this. There has been some, yeah. Then we came to the implementation of level 1 in the linear region and saturation region. In linear region, you see that it is the same expression, only modified by this multiplier term 1 plus lambda VDS to account for the channel length modulation with VDS. So lambda is a factor, is a parameter which is a channel length modulation parameter. Its default value lambda is equal to 0 means neglecting the channel length modulation. It is valid for very long channel devices. And threshold voltage in level is ultimately normally denoted by something like this, which was already defined in some earlier class while discussing the device physics, where VTO is a threshold voltage without the body effect. The BBS is equal to 0 means without the body effect. XJ1 is the lateral diffusion parameter, and gamma is normally called the substrate bias parameter. It influences the substrate bias. This is for the linear region, and the saturation region in the same way. And another thing you note that instead of writing L effective, we write L minus 2xj1, so that L and xj1 are two model parameters, or rather they are obtained simply from the geometry of the mass of the devices. Then in saturation, for which of course always VGS is greater than VTH, but VDS exceeds VGS minus VTH, the equation looks like this, where again this parameter 1 plus lambda VTS counts to account for the channel length modulation effect. And I said that ultimately level 1 has got so many parameters like Kp, gamma, 2 phi p or phi p, Cox dash, per unit area capacitance, lambda is that channel length modulation parameter, xj1 and L are geometrical parameters. And I mentioned the typical values, something like this, and I requested you to develop this model. Okay? Okay, yes. And we have shown that using this model, typical results are like this. Simple level 1, which is rather simple but quite educative and quite helpful in quick evaluation of MOSFET characteristics. May not be very, very accurate, but they serve the purpose in many cases where a quick computation is needed. This is a plot of the transfer, this is called transfer characteristics, ID versus VGS. For two values of VBA, the substrate bias. Without substrate bias, it is designed for threshold voltage 1 volt, but then with increasing VGS, you know that it starts from 1 volt and gradually increases. And with the changed values of Kp, this is for Kp higher value, and this is for, sorry, this is just reversed. I have written the reverse values. This is a lower value of Kp, and this for the higher value of Kp. I should be, Kp is equal to mu C, or where mu is more here. I have just written the opposite values. With higher values of Kp, you find an increased value of Gm. Gm is nothing but delta ID divided by delta Vg, which is expected. And similarly, the ID VDS characteristics called output characteristics of the MOSFET were also obtained for different values of VGS. Here, of course, lambda has been taken to be 0, but you can take suitable values of lambda to match with experimental results, particularly to account for the channel length modulation effect. Level 1 will not match very well with experimental, which is expected. It will match, but not match very, very exactly, and therefore higher order level, these things came, and it is very clearly indicated here. Then we came to the level 2, which was due to John Meyer, just almost within 2-3 years of the development of level 1, I told you that these levels of MOSFET models came along with the technology development because the dimensions gradually shrank. From so-called very long channel, it became long channel, then gradually towards short channel, and ultimately towards very short channel. That's how the technology got developed. Level 2, as I already mentioned, the level 2 assumes that the drain-induced depletion is actually, because of the drain voltage, because of the current flow, there will be a surface potential due to the lateral potential drop, and that will enhance the depletion layer, which is otherwise depletion layer is saturated to a value corresponding to the surface potential equal to twice 5 approximately. But this extra potential which is developed at the surface with respect to the source due to the current flow from source towards the drain, that adds up to psi s, and that's how we get a deeper depletion as we approach from source towards drain. Okay, and that is taken into account in the second model, and therefore the second model definitely is better and more accurate. And in this evaluation, you see that a differential charge in an element of thickness dx, if you consider a channel of thickness dx at the depth x from the surface, the elementary charge, or the differential charge, is now related to the same kind of old expression. Only thing is that in twice phi p minus VBS is the usual thing. If I ignore the drain-induced depletion, but taking into account the effect of drain-induced depletion, this plus VCX term comes, which is the channel potential at x with respect to the source. And ultimately, this was derived earlier. Same, we also in the device physics, we discussed the same models, but a little bit more. We did the derivations. Here we avoided the derivations. Ultimately, we get an expression for IDS, which looks like this, which is different from the earlier one. And we may note with care that here this gamma has come, which was not there earlier. The IDS expression for the level 1 was independent of this term. Now this has come. So Na, etc., substrate doping, dielectric constant, etc., they come into picture and modifies the current in the second model, which should be. In fact, which was obtained earlier. There was definitely some major incorrectness, but taking into account that. So you know what? How did I get? This is the general expression for IDS we got, which is valid for the linear region. But then, how did we set the VD sat, or this onset of saturation? Here we assume that at Qi at L dash, the inversion charge density at L dash, the point of pinch off, is 0, which was not the assumption earlier. Earlier case, we simply assume it was 0, but VD sat is equal to VGS minus VTH. But in this case, we do not do that. We assume that Qi at L dash is 0, and that results into an equation like this. That happens when VD is equal to VD sat. I assume that Qi at L dash or L becomes 0 when VD is equal to VD sat, so that we get an equation like this, by solving which we can get an expression for VD sat. That's how we get VD sat. VD sat is the drain voltage at which the saturation just starts. How do we get that is why, that this is the thing. This is of course the expression for IDS, and that is how we set the condition for saturation. Then in level 2, the VTO is further written like this. Normally in level 1 we just give an assigned value of VTO, but now VTO is given a physical thing where VTO is given by phi ms. Instead of writing that QB dot Q0 dash by CO is dash, we write QNSS. So we bring in another parameter NSS, which is nothing but surface density, state density located in the offside. So that this multiplies by Q is nothing but the fixed offside charge. and we write it in this particular fashion where phi m is, this is very clear, this VTO expression is just the derived expression. Only thing, instead of QF by COX we write minus Q NSS dashed by COX dashed. This dashed, of course, there is a significance. When we put the prime, it means per unit area, per unit surface area value. If we do not put the prime, it is the total number of the surface. Please remember, COX without prime is undashed COX is the total oxide capacitance, whereas COX dashed is oxide capacitance per. Similarly for NSS dashed. And this TPG parameter which is there in phi ms, here phi ms also has been modeled physically. And there I discussed in the last class that this TPG is a tri-state parameter, 0, -1, +1. 0 for metal gate, particularly for aluminum gate, for which phi m is approximately equal to chi s. Okay, -1 for poly gate doped with the same type of material impurity, and +1 for poly gate doped with the opposite impurity. I asked you to verify it yourselves. Okay, why it is so? That I think you have to verify it yourself. There is nothing. Then we consider the linear region, and such for the implementation of level 2, we consider the linear region and the saturation region. Here, linear region is the region for which VGS is greater than VTH and VDS is less than VDZ as before, as in level 1. Whereas in saturation region also as before, VGS is more than VTH and VDS is more than VDSat. We get these two expressions for IDS. This is the IDS expression for the linear region. Note that instead of using the multiplier 1 plus lambda VDS, here we have used a divider which is 1 minus lambda VDS. In fact, it has been found that it helps in fitting better with the experimental characteristics. So otherwise, this is the same expression as derived earlier, just shown earlier. Only thing is, it has now been expressed in terms of the parameters which are included in the SPICE list, SPICE Kp, W, etc., etc., and 1 minus lambda VDS. In the saturation region, now the current is expressed as I dsat multiplied by again 1 upon 1 minus lambda. That is the same divider. 1 minus lambda VDS is used once again in addition to the one here. That helps in better fitting, as if in the drain saturation region it becomes square, 1 minus lambda VDS square, whereas ID sat is nothing but the value of ID obtained from this linear expression substituting VD is equal to VD sat, where VD sat is obtained by solving this equation, which I have already told you, by solving this equation, this equal to 0. Using this, solving this equation, whatever value of VD we get, for that value of VD set, what is the value of IDS? That is the ID set, but it is further increased slowly because of the channel length modulation, and it becomes 1 minus lambda VDS. So we discussed up to this in the last class. Now consider some of the, gradually in the, that level 2 models are made more and more accurate. This is the basic model, basic level 2, whatever I have discussed. Now certain further modifications are incorporated to make the level 2 more perfect. Okay, the first one is the dependence of mu on vertical field, which I have discussed, you remember, while describing the device physics. Here, because mu is definitely Kp is equal to mu Co is dash, so Kp is modified. So in the modified form, Kp, which I write as Kp dash, this is a modified value of Kp, and that is equal to Kp. Kp means that simply mu into Cox dashed. Okay, but there is a multiplier now, that is epsilon s by epsilon Ox into different, a number of parameters are brought in, Okay. Here you see that this term UC that we have brought in while modifying Kp. This is the Qp where Kp is simply equal to the old expression, but effectively Kp is changed because mobility is modified. Mobility is not a constant. In practice, mobility depends on lateral field as well as vertical field. Of course, in this case, we are considering only the lateral vertical field effect. Mobility, as the electrons are moving along the channel and there is a gate-induced vertical field, their mobility or their velocity is reduced. Effectively, mobility is reduced. Okay, that mobility I discussed earlier. Some model a simple model I have given while describing the device physics. But in SPICE, it is usually modeled like this in SPICE level 2. Kp, instead of directly writing mu Cox dash, you write mu Cox dash multiplied by this factor, where you see that I have brought in three parameters: UC, UT, and UE. UC, UT, and UE. If you carefully see, then VGS minus VTH minus UT VDS divided by TOX is nothing but the average electric field perpendicular to the channel. And where this UT is called transverse field coefficient. This is a SPICE parameter. If you neglect the effect of VDS, then the normal component of electric field is nothing but VGS minus VTH divided by TOX. That is the field over the semiconductor. Okay. All right. Whereas, because of the channel potential, this is modified. Because of the channel potential, this is modified, and that is taken into account through this a term which is proportional to VDS minus a term which is proportional to VDS. The coefficient, we call it UT, it is an adjustable parameter. Please remember, these models are semi-empirical in nature. They are not very, very exact. To some extent, they are derived analytically. Some extent, they are modified through intuitively. We make many, many approximations. We introduce a lot of, I should say, that empirical relations. But then behind them, always there should be some physical thinking. Suddenly you cannot write something. For example, it happens because of VD, the channel potential, the vertical component average field will be modified. Average field normal to the channel will be modified by the drain bias. So there should be a term, and that term is modified again by a term coefficient which is UT, and that has been called transverse field coefficient in this thing. UC, if you see carefully, UC is nothing but the gate to channel critical field. Above which mobility starts falling. we assume that up to a certain transverse field, by transverse I mean perpendicular, lateral is along the channel and transverse is perpendicular, okay. So UC is again another spice parameter for level 2. We assume, this is a very, of course, not a very correct assumption. It's not true that up to a certain field there will be no velocity change. Rather, the velocity will slowly change. But here we are assuming that up to a certain critical field, the velocity will not change, mobility will not be affected. On the other hand, as that critical field is exceeded, the mobility starts falling. That critical field. So can you tell me that is critical field is UC. So what is this term? This term is nothing but therefore UC is the critical field divided by BGS minus VD divided by 2x. That means critical field divided by average field. The second term is nothing but the critical field divided by the average field. And of course, this epsilon s and divided by epsilon ox term has come because of the effective dielectric constant. This is again, let me tell you, is an empirical, semi-empirical derivation. But then, what should be the power here, the exponent here? U is called exponential should have been called exponent. Anyway, exponential coefficient for mobility. It is a spice parameter. Its value lies between 0 and roughly 0.1 typically. If it is 0, then no, we are not considering. If it is 0 means this term is 1. So we are not considering the effect. But it is less than 1, then definitely we are considering the effect. Anyway, please remember, these are fitting parameters. You may ask me a lot of questions after that, why you are unnecessarily introducing so many fitting parameters. That has to be discussed and understood. I'll explain it afterward. Then, you know, the level 2 also considers, I'm continuing level 2. The subthreshold conduction, weak inversion design. That is considered in level 2. Now, to consider the weak inversion, we define a voltage, we call it VUN. This is the voltage for the onset of strong inversion. VTH is the threshold voltage for the onset of inversion. But we define VUN, a voltage for strong inversion. So this VUH is the voltage for strong inversion. And that we define, I have already indicated that earlier while describing the physics. Some people call it 2 kT, 3 kT, 6 kT, it depends. You know that typically 6 kT by Q is quite often used. But here they model the N value. Instead of writing some 1, 2, 3, 4, the N is physically modeled through this equation. Let me put a prime here, that will be good. Let me repeat once again. We, for the subthreshold conduction current modeling, that means current under weak inversion condition, modeling that current, we define a voltage for strong inversion like this, where n is again a parameter which is derived from number of parameters which are spice parameters. Say for example, this is that is expected. There is nothing special. You know that this equation is a derived equation. We are not going into the detail, otherwise you cannot finish the course. It's a very big subject. It is usually n is equal to, this term can be neglected. Then it is simply Vt. Then it's just inversion. But what happens, just like our diode conduction, semiconductor p-n junction, up to V gamma the current is so small. Thereafter it starts actually switching on. Okay. Here also we say it is, you remember the plot of Qs versus psi s, which was derived in the class, and I showed the nature of Qs versus psi f characteristic. And there you have, I think you remember that certain regions Qs was changing slowly. You remember the accumulation region, as you go make it negative gate bias, the charge increases fantastically at high speed, exponentially. Then as you apply a positive gate bias for NMOS, the surface charge increases slowly, following a square root law. Then as the substrate potential QS, psi s, the surface potential exceeds that twice phi f kind of criterion, then again there is an exponential rate of rise of charge, the surface charge with psi s. And that very fast rise we actually approximate as almost a constant. That means we assume psi s becomes almost constant and independent of psi s, and that happens at psi s is equal to twice. It's not exactly true. There is an exponential rise, you remember. Here also, that this thing that is exactly at the threshold voltage, the inversion, yeah, we get a number density at the surface of electrons, which is the same as that in the bulk. I remember that. When psi s is equal to twice phi f, n at the surface becomes equal to the p at the bulk for an NMOS. That means for a p-type substrate. Okay, but that n over, and what is the typical thickness of the inversion there? It's very small, 50 to 100 angstrom, maximum 150 angstrom. Over that n, which is of the order of 10 to the 15 or 16, the channel conductance is extremely low. With that n, suppose p is equal to 10 to the 16, at psi s is equal to twice phi f, the surface n, the n electron concentration at the surface become again 10 to the 16. But what is the thickness of the inversion there? Very small. It's a two-dimensional electron gas. It is a potential well. I told you, quantum well. It is so thin. Okay, and then the conductance of the layer formed by the inversion at the just onset of inversion is still very high. The current will be very small. It will remain in the range of nanoamperes to microamp, maximum 1 microampere of that order. But we have to go towards milliampere, because unless you come to an order of at least 0.1 milliampere, normally the devices are not on. Okay, so Over that region, if you remember the ID versus VGS characteristics subthreshold, there is a slope. Gradually it reaches the milliampere from from nanoampere to gradually to milliampere. Over that region, therefore, we have to define a voltage for which we can say reliably, yes, the transistor is on. That is why what we do, we add several thermal voltages with VTH. VTH is the onset of voltage, onset of threshold, but then KT by Q is the thermal voltage. So NKT means N VTH. That VTH means V small t small h, thermal voltage. And that N can be approximated by a formula like this, which I am not deriving here. And here, what is NFS? NFS is a fast interface that SPICE defined, but actually this is nothing but DIT. Integral of DIT over the band gap. That means QIT by Q. That means QIT by Q. Okay? And what is CD dash? CD dash is the depletion layer capacitance. CD dash by COX dash is nothing but the ratio of the depletion layer capacitance to the oxide capacitance. And that depletion layer capacitance is given by this simple formula, which you remember. Gamma is nothing but root over twice epsilon s by QNA. So this is the value for VUN. This VUN is defined because we now write for current in weak inversion that means what is weak inversion? According to my definition now, weak inversion is defined as this, not VTH. Current in weak inversion means current for values of VDS less than VON. This IDS in weak inversion. Remember that in level 1, the subthreshold current was neglected, was assumed to be 0, but here it is not 0, and that is equal to I on multiplied by an exponential factor, which is so weak inversion regime now. In fact, level 2 can compute the current in the weak inversion condition also, and it is modeled like this, where IDS in weak inversion is ION. ION is nothing but IDS for VDS is equal to VON. Same VDS, IDS expression, whatever you have derived, you use it, but put for VDS VON. VON is obtained from here. So put that VON, get the current, multiply it by the exponential of VGS, the difference of how much, it is nothing but exponential Q by KT into VGS minus VON, how much, and that is typical for the diffusion current. You remember the subthreshold conduction is primarily due to the diffusion of carriers. Not drift of the carriers is not important in subthreshold because the current is very small, potential drop is small. The potential gradient along the channel is very small in the subthreshold design, but it is a diffusion of current because already subthreshold means still you have reduced the barrier at the source. Your surface potential is not twice phi f, but you have reduced the barrier at the source. Barrier at the source was VBI. Now the barrier is VBI minus psi s. Psi s is not twice phi f, less than, but the barrier has been reduced. Electrons will be injected from the source into the channel. But in the channel, because no inversion layer is formed so much, so there is no field felt. You are applying a voltage at the drain, but the overall channel resistance is so high that the electric field in the channel is negligible. But then how the carriers will move? Simply by the action of diffusion, because there are more electrons injected from the source than from the drain side, so there is a diffusion of carriers. So it will behave just as, that is what I discussed earlier. That is how we derived the expression for the drain current in the subthreshold design earlier. So, but this is a simplified model. The model which we derived, the equation which we derived earlier in the device physics class was a little bit more rigorous, but this one is rather simple. And you know that gradually the MOS models were rectified, modified, not in one step, several steps. In level 2, it was like this. So that's how, but in doing so, there is a problem. Let me tell you what is the problem with this part. You see, suppose this is the ID now versus say VDS. In VDS scale now there is a button rather for VGS. For a given value of VDS, say VDS is equal to say 1 volt. VDS is equal to 1 volt. So what is expected? You expect a curve like this, isn't it? We expect a curve simple like this, which I have already done. For a certain value, say VBS is equal to 0. So subtracted by it is 0. This is the kind of curve we showed earlier, isn't it? But you remember that we can write a value, a voltage here, which is we have already defined, that is V1. We know what is the value of V1 from this equation. So at that V1, you will get a current. And from which model you are getting this current? From which model you are getting this current? You just see this equation. I1 is equal to IDS when VDS is equal to V1. But what is the equation for IDS you are considering? We are considering the old equation, that is the standard, this equation. Standard model equation for computing the current, okay? So you are getting, so this part of the characteristic, you are getting from that equation, using this equation. Above V1. But below VN, which equation you are using? You are using this equation. So you are getting a characteristic like this, maybe in the exponential scale. So, say 10 minus 9, 10 minus 8, 10 minus 7, 10 minus 6, 10 minus 5, and so on and so forth. And this is in volt, maybe it may be say 0 volt, 2 volt, 4 volt, 6 volt, and so on and so forth. Say VON may be 2 volt. For VON, as calculated from this equation, may be 2 volt. This equation may be 2 volt. So you see that the portion of the curve above VON may look like this, whereas the portion of the curve below VON will be more or less a straight line in the semi-log graph, because it is an exponential equation, logarithmic. Okay. So what is expected? The curve, the slope continuity, there will be a continuity of curve, but the slope continuity will not be there. Slope continuity, at this point, the slope obtained from this equation, and from this curve, the slope obtained from this equation, they may not be matched. Slope will not be equal. That is a problem. In fact, any physical system, We have to see that continuity is being maintained both in values as well as in first derivative. If possible in second and third derivatives also, for smooth transfer. Because that's nature. Natural process is always like this. Is always like this. When a variable y, dependent variable y, anything, varies with an independent variable x, usually the variation in nature, MOSFET is a natural device, isn't it? So it should vary in such a way that both the value of the function as well as its derivative should be continuous. But that will not take place in this case. There is a problem in this. And in fact, something has been done that I shall not discuss, by some other workers did some work to make it smooth. It can be done. Instead of using straightforward exponential, you do something mathematically so that the slope also matches. It is not only the functional values, but also the slope values also match. So this is regarding the subthreshold conduction in the N-channel MOSFET. Next comes variation of channel length. Variation of channel length. That is channel length modulation. Channel length modulation. We have introduced the term lambda, isn't it? But then you see that there is an L dash term. L dash is the reduced channel length at which the pinch off occurs. That can be written as L effective into 1 minus lambda VDS. You just compare the two equations. So now L effective has been replaced by some in the denominator 1 minus lambda VDS, isn't it? It's just the two. Instead of writing that 1 plus lambda VDS, what we are writing, W by L effective or L plus L minus 2xg1 multiplied by 1 minus lambda VDS. And this gives a value of lambda which is equal to L effective minus L dash divided by L effective into VDS, where L effective minus L dash is something, if we can obtain, then you can calculate the value of lambda, and that is in level 2 is expressed like this. So what has been done is, there is a, now lambda can also be calculated. You see that I have given you a formula for calculating L effective minus L dash. Okay, a formula for calculating L effective minus L dash has been given.